Even before these experimental developments, mathematicians and mathematical crystallographers were studying the symmetry of periodically arranged points in three-dimensional space. They came up with numbers like 32 point groups, 14 space lattices, and 230 space groups. We will not be concerned with these numbers here, but look at one important kind of symmetry which crystals have. This is the rotational symmetry. Now this interesting swastika comes into self-coincidence if it is rotated by 90 degrees about an axis passing through its center. In one complete rotation, it will come into self-coincidence 4 times. We say that it has 4-fold axis of symmetry, or simply a 4-fold symmetry. Atomic arrangements in crystals also have these kinds of symmetry. The rotational symmetry of finite objects can be of various types. Here some examples are shown. Objects of 2-fold, 3-fold, 4-fold, 5-fold, 6 and 8-fold symmetries are shown here. So flower with 5 petals will have a nice 5-fold symmetry. There is an interesting theorem of crystallography, well known as crystallographic restriction, which says that the periodicity of a crystal restricts the rotational symmetry it can have. For example, a crystal cannot have 5-fold symmetry, and also it cannot have any symmetry more than 6-fold. So only possible symmetries, rotational symmetry which a crystal can have, is 2, 3, 4 and 6. Of course, 1-fold is equivalent to 0 of symmetry, that is no symmetry. Now let us look at another important and a very critical experimental development which was required for the discovery of quasicrystals. In 1924, de Broglie postulated wave-like nature for electrons. Then 3 years later, Davison and Germer and G.P. Thomson experimentally demonstrated that it's actually possible for electrons to diffract. Finally, in 1931, Ernst Ruska and Max Knoll developed an extremely important equipment for material scientists and crystallographers, and that was electron microscope. The power of electron microscope is that you can combine microscopy with diffraction, and the electron diffraction pattern from an amorphous solid and a crystalline solid are very distinct, as is seen in this example. From an amorphous solid, you only see a diffuse halo, whereas from a crystalline solid, you see nice discrete diffraction spots. It was thus understood that crystalline materials have periodic arrangement of atoms and give discrete diffraction patterns. All these 3 terms, loosely speaking, were considered to be equivalent: crystalline, periodic arrangement of atoms, and discrete diffraction patterns. Amorphous, on the other hand, had a random arrangement of atoms and gave a diffuse diffraction pattern. This would be a diffuse diffraction pattern. Now, electron diffraction has a great power to show the symmetry of the crystal. For example, if we have a cubic crystal and its beam is traveling parallel to the edge of the cube, which represents 4-fold axis for a cubic symmetry, then the diffraction pattern here also shows the 4-fold symmetry. Similarly, if the beam, the red beam, is traveling along the body diagonal of a cube represents 3-fold axis, so the diffraction pattern also shows a 3-fold symmetry. In fact, 3-fold doubles up as 6-fold, and that's why you see a hexagon here instead of a triangle. This is true always in electron diffraction pattern, that odd symmetry are doubled up. So in 1980, crystallography was a well-established closed science. Definition of crystal as periodic arrangement of atoms was well established. Symmetry theory was used to classify the crystals on the basis of symmetry, and important theorems like impossibility of 5-fold was proved, and experimental tools to determine the crystal structure were now well established. Crystallographers not only had X-ray but also electron diffraction. But in 1982, while working with an aluminium manganese alloy, Dan Schuttman was surprised to get a diffraction pattern shown here. It's immediately obvious that diffraction pattern is consisting of discrete diffraction spots. Thus, it should come from a crystalline material. But then, when Schuttman looked closely, around the central spot, you have rings of 10 bright spots. So it should represent a 10-fold symmetry. And now, just as we have discussed, 10-fold symmetry is not possible for crystalline structure. So this was Schuttman's dilemma. Discrete diffraction pattern indicating to him that he is working with a crystalline material, but 10-fold symmetry telling him from the well-established theorems of crystallography that the material he is working with is not crystalline. So what it is? He was surprised. Here is his copy of his original notebook showing here that he was surprised to have a 10-fold symmetry. He has put up 1 exclamation mark followed by 2 question marks. Very, very, very surprised. It took him 2 years to work out the details of this, and finally he published a paper in Physical Review Letter entitled Metallic Phase with Long-Range Orientational Order and No Translational Symmetry. What he established was that periodicity is not necessary for sharp diffraction pattern. Lack of periodicity does not mean lack of order. There is other kind of order, that is quasi-periodic translational order, which can have 5-fold symmetry. Such crystals were called quasicrystals. Thus, his 1984 paper finally led to reclassification of solids, not only as crystals and amorphous, but crystals, quasicrystals, and amorphous. A new phase, quasicrystal, was discovered, which, despite giving discrete diffraction pattern, is not crystalline but is quasicrystalline. About 8 years later, the International Union of Crystallography actually included these aperiodic crystal or quasicrystal as a kind of crystal. So they redefined crystal as not ones having periodic arrangement of atoms, but ones which give discrete diffraction pattern. So finally, we conclude with a list of crystallographic revolutions. The first revolution was the first definition of crystal, that crystals are solids with regular external shape, and Kepler and Hooke's hypothesis that this regular external shape may be because of internal periodic arrangement of atoms, which was finally proved by von Laue in 1912. 1914 he got the Nobel Prize. Von Laue in 1912, where through his great experiment, he showed that actually crystals are periodic, and as a byproduct he also proved that X-rays are waves. And the final revolution, which is the subject of this Nobel Prize, is by Dan Schuttman, who through his 1982 experiment showed that there are crystals which may not have periodic arrangement of atoms but quasi-periodic arrangement of atoms and still give sharp diffraction pattern. Of course, he had to face a lot of struggle in getting his idea accepted, and so I end with a quotation from him where he says, "If you are a scientist and believe in your results, then fight for the truth. Listen to others, but fight for what you believe in."